Hello everyone. In this tutorial I'll be talking about the MNIST database or the MNIST handwritten digits, and I'll be using Keras to develop a neural network model on this data. So the MNIST database of handwritten digits is basically a training set of 60,000 examples and a test set of 10,000 examples. It's basically handwritten digits, and the images are basically 28 by 28 pixel, and each image is basically classified into one of the 10 classes from 0 to 9. If you will see, this is quite like hello world for the neural network model, and when I will be putting up some tutorials on convolution neural network, Jan LeCun, Corina Cortez and Christopher J.C. Burgess have made this available to us. And Jan LeCun was the one that developed the convolution neural network model, and as of today this is the best performing model. It has an error rate of 0.23, and if you would like to read the paper, this is the link that you can go. This is the link for this website. Now let's jump into the Keras tutorial. So for this particular example tutorial, we will be needing the MNIST data set. The good news is Keras comes with this data. If you are doing this for the first time, it will download the data from an Amazon repo. If you have already done that, then it will be saved somewhere in the local and it will be loaded from that. We also need the sequential API because that is something that we'll be using, and again we'll be just using the dense layer. There is something more that we'll talk about is something called overfitting, and to prevent overfitting we'll be using something called Dropout. Then we will also be using Keras classifier. This is a wrapper on top of the Keras to make it compatible with scikit-learn, and we'll be using grid search CV to tune the parameters. As we noticed last time, there are multiple parameters and we can tune some of them to get the best model out of it. We will be using the matplotlib for some plotting, and then we'll be using the grid search CV from a scikit-learn for tuning the parameters. For those of you who don't know what sklearn is, scikit-learn is basically one of the most used Python machine learning frameworks, and it's really good. If you have not used it, I will suggest you start with that. If you do not know how to install scikit-learn, this is how you need to install. Sudo pip3 installs sklearn. This is the link that I was looking before. We will be going in for 10 epochs and the batch size is 128. The classes are from 0 to 9, so there are 10 classes. The number of hidden neurons for now is 256. The validation set will be 0.25, and this is how we will load the data. So MNIST.loadData basically returns a tuple, and this tuple basically will be xtrain and ytrain and xtest and ytest. So now this is done, and this is using TensorFlow backend because this is what we had done initially, and we'll take a look at some of the example digits in this. So the first example, this is a 28 by 28 pixel image, as we can see, and this is a 5, and the correct label also says 5. This is a 0 and it also looks like a 0. This is a 4 and it's also a 4. This is 1. It looks like 1 and is 1. Then this is a 9. It also is 9. This is 7. This is 2, and this is a 1, and this is 0, 4. And so these are randomly chosen images from the training and test set. As we saw earlier, we have 60,000 examples in the training set and 10,000 examples in the test set, Each of these images are 28 by 28 pixel, and this is the shape that we can see here. Since we're using the dense layer, we need to reshape from a 28 by 28 pixel image to a linear vector. For that, we'll be using something called reshape that comes with the numpy, and then once we do that, we will be normalizing the pixel values by dividing by 255, because the maximum value that a pixel can take is 255, and so everything will be between 0 and 1, and we need to convert that to a float 32. For the since I'll be using the categorical cross entropy, so that's why we need to convert that our y values or the actual labels to a one-hot encoded format, and we will be using the np utils from to categorical from Keras to do that. So once we have reshaped our data, we can see that before our data was 28 by 28, now it's just one vector, 784 length. Let's say what our data looks like. So as we can see, the data contains mostly zeros, a sparse matrix with some values, and these values basically are the intensity, and the actual label of this is 0 1 2 3 4 5. So this is a 6. We will be initializing a model, and for now what I will do is basically, to make things easier, I have made a function. This function name is make model, and it takes one input parameter called number of layers in the model. It initializes as the sequential model to a variable called model, and if we have given the number of layers as 0, which means that there's just one output layer, then what it does, it just defines one output layer with a dense layer, and the output dimensions has to be the number of classes. There's no other thing that we need to do, and the input dimension we need to provide here. As you might remember, the first layer needs to have this input dimension, and the further layers will automatically have that. So the input dimension will be the xtrain dot shape and 1. So if you remember for the last time, the shape of the data is basically 784, and this is the what it will be here, and the activation function will be the softmax, since we need the probabilities for 0 to 9, and then we need to we'll compile the model using the loss of categorical cross entropy and the SGD optimizer and accuracy metrics. We'll return the model. If this is not the case, then what we will do is basically we will add models. So for the first layer, we need to provide the input shape and the output shape. Otherwise, we do not need to provide the input shape everywhere. The activation function will be relu here, and once we have added everything, then we will basically add a dense layer with an activation of softmax, and then we'll compile the model and return the model. So as I said, the xtrain shape 1 is basically 784. Now what I will do is basically let's initialize the model with 0 layers, so there's just one output layer, and print model.summary will basically give the layer the number of layers and the number of parameters in our layer, and then we will fit the model to xtrain and ytrain on the batch size that we defined above and the number of epochs we defined above. And validation split is basically this Keras will split the data into 75 and 25, and it will train on the 75 and it will check the accuracy on 25. This will be helpful to know if our model will start overfitting or not. As we will see later, as we increase the number of layers, the model will start to overfit, and we will see how we can determine that. So once we run that, this is the print of the model.summary, and we can see we have just one dense layer with 7850 parameters, and then all of them are trainable parameters, and we are training for 10 epochs. So for the first epoch, we can see in the very first epoch we are getting high accuracy. Now this the accuracy on the training set is 0.67 and the accuracy on our validation set is 0.8264. This can either mean that this is either underfitting because it has not seen all the data, so it might be underfitting, and as we move forward we can see that the training accuracy has jumped significantly, and now it is very close to our validation accuracy. And as we move forward, in the final epoch we have the training accuracy as 0.8860 and the validation accuracy as 0.8919. So now these two are quite close to each other, and we can say that our model is quite confident, and the accuracies on the training and the validation are quite good, and it can generalize. Let's plot the validation loss, the validation accuracy, the training loss, and training accuracy. As we can see, this is the training loss. So, and on the x-axis we have the number of epochs. So as we can see, it drastically reduces till the second epoch, and then it has started to plateau down. Now after this, even if we have to go to 1000 iterations, the loss will not reduce significantly because we do not have more number of parameters to tune. So we can say that the model that we have, it just has 7850 or around 8000 parameters, and it's not so complex. So what we can see that our training accuracy and validation accuracy jumped a little bit, but they have plateaued down, and this also says that this model cannot do any more than that. So let's see what happens if we increase the number of layers to 5. When we do that, then what happens, as we can see, is we have 1 2 3 4 5 layers, and then followed by a softmax layer, and total parameters now is 466,698. So initially we had 7850 parameters, and now we have 466,698 parameters. That is a huge jump. Now obviously this will further better our model because we have more things to tune, but it will also have it might also have an effect on our overfitting. So let's see if our model has overfitted or not. So this is the first epoch that it has trained, and it's training on 45,000 examples and validation on 15,000 examples. So in the first epoch, as we can see, it took 125 microsecond per step. So the step size is basically of 128, and the loss basically is 1.8, and the accuracy is 0.43 on the training set, and the 0.7804 on the test set. And as we move to the last epoch, the accuracy on the training set is 0.9466, and the validation set is 9379. As you can see, just going from 1 to 5 has given us a performance boost in terms of accuracy by almost 4 to 5%, and that is a huge jump, and this is significant to the number of layers that we increase. But if we can see that it has again plateaued down, and then even if we go more than 10 epochs, it won't increase, the accuracy won't increase significantly. And again, this is basically a reflection on that our model is still not able to understand everything in our data. There are several things that we can do, like for example, we can try to play with the layers, or maybe we can jump to the convolution neural network to do that. We can also try to increase the number of epochs. So in this in the next example, what we'll do is basically have increased the number of layers to 10 and the number of epochs to 5 into 10, so 50 epochs. And let's say now what happens. So when we do that, now we have 10 layers, in our model, and then we have 795,658 total weights that needs to be tuned, and these are all trainable parameters. What will happen is, as you can see in the first epoch, now the validation accuracy is 0.2737, and for the training accuracy is 0.2458. This is significantly lower than what we had previously, and this basically gives an idea that now it has to do more work to tune all these weights that we have, because they have been randomly initialized, and then it has to go all 50 iterations. But as we can see, just in the 5th iteration it has reached a respectable value, so that on the training set the accuracy is 0.8867, and on the validation set the accuracy is 0.9, and in the 8th iteration the accuracy has jumped to around 0.94, and on validation it's around the same. So this is something that we should be looking at. We can see that the data has not overfitted here. If we have this value and this value quite significantly different from each other, then we can understand either there's overfitting or there might be an underfitting. In case of underfitting, what will happen is, let's say we just train for one epoch, then within just one epoch what might happen is the model will not be able to learn all the patterns in the data, and it will underfit. But in what we're doing now is we are training for 50 epoch. In this, basically sometimes the model will start to learn the noise in the data, and it will not be able to generalize for out of sample data or the validation data. So for example, here now the training accuracy has been 0.9674, but the validation accuracy is just 0.9519, and we can see that the model might have started to overfit. And let's see if that's the case. The next iteration, the training accuracy is 0.9712, and the validation accuracy is 0.9528. Surely our model is overfitting. Ideally, what we should have done is we should have stopped our training somewhere here or here. There is a early stopping criteria which I'll be talking in the later part of the course, but because we don't need all this. First of all, now any more training that we do is not helpful, because this will give us an overfitted model, and we should have stopped here. But still, what we found was, just by increasing the number of layers by 5 and doing more epochs, gave us a performance boost by almost 1% if we had stopped there. But then if we go beyond that, we saw that the model becomes too complex, and it won't be able to handle the overfitting, and it will start overfitting. So what we'll do is, basically it's still in the 24th epoch. I will pause the model, or what I will try to basically give an idea about this. So you can also download this and play with this. You can use NumPy to load this, and this is exactly the same thing that comes with Keras. And you can read some of the papers that people have written with their layers architecture. One of the things that I would advise is reading the architecture that people have used, which actually sometimes is very, very helpful when you're designing your own layers. And we can see that they have used some sort of CNN. And what I'll do is, basically I'll pause the video for some time and then resume when this is done. the training has been done. In the last epoch, we can see that the training accuracy is almost 0.9999, and the validation accuracy is 0.9675. This totally reflects the fact that our model has overfitted and that we cannot rely on the model. We should have stopped somewhere earlier, around maybe the 10th epoch. So I don't think the training after that makes any sense, and the graph also reflects the same fact. Now we have seen that there are many parameters to tune, and what Keras has provided is a wrapper for scikit-learn, so that we can use a grid search CV on this model to tune one of parameters. So this is the documentation for this, and this can be only used with sequential model with single input only, and this is a limitation because if you remember, the grid search takes only one input and one output, one X and one Y. When we'll be looking at the functional API of Keras, we will note that there is a possibility of taking multiple inputs at a time, but since scikit-learn cannot handle, so that's why this wrapper also cannot handle. And there are two wrappers available, one for classifier and one for regressor, and there are two arguments that it takes. The one is a build function, and this is a callable function, and it should instantiate our class, sequential class, add the layers that we want, and then compile it and return back the compiled model. And the sk_params is basically the parameters and the fitting parameters that we want. So for now, what I will try to do is basically, let's say whether it's good to have one layer or two layer, and basically the build fun, as I said, is make model that we had above, and we're just doing for one epoch, and the batch size, let's say, remains the same, and the verbosity is 2, and then we instantiate the grid search CV using this estimator that we just built from the Keras classifier, and the parameters grid we have. Do remember that when I experimented with njobs is equal to -1, my job was freezing, so I had to use njobs is equal to 1, and the cross validation here is 5. So when I fit, is basically it starts fitting the data and it gives the output for this. So we can see on the first CV for number of layers, for the first epoch the accuracy was 0.704, and since we're just training for one epoch, we are not expecting a really awesome accuracy that we have seen before, but this is just to give an idea that we can use this Keras classifier, that is the wrapper of Keras model for scikit-learn to tune the parameters, and once the training is done, this will give an output. So the best model accuracy was 0.84, which is quite close to the initial model that we had, and this was on the two layers. So as we can see here, is having more layers is obviously better, but then as we increase the number of layers, it's not totally right to say that the accuracy will keep increasing. It will increasing, but somewhere the model will fit. Now I wrote another function. Now what I'm trying to do is, whatever parameters we need to optimize, this function should take that as a parameter. If it doesn't, then it won't be able to the grid search, the Keras classifier won't be able to fit that. So here we have everything have the same, but apart from everything else that we had, we are also having number of hidden neurons to optimize, so we will experiment with that, and we have something called dropout. So dropout is a way of controlling the overfitting, and this is a layer. So dropouts consists in random setting. So at randomly a fraction of the neurons will be set to 0, and using this what happens is the model does not overfit. So for example, let's say if you have to go from point A to point B, and you are going there, you're using a route every day. So what might happen is, if tomorrow something happens in that route, you might not know any new route. So what this does is basically it will randomly put some neurons, some weights to 0, so that this model does not learn noise as well. And then the parameters needs to pass in the same way, and everything remains the same that from before. And we have increased the number of epochs to 3. So this is exactly the same thing from before. And this basically concludes my experiments with dense layers on MNIST. When I start with the convolution neural network, I'll be basically, we can see that we can increase the accuracy to more using different things. So this will take a little bit of time. And as we can see, this is basically training on all 3 combinations: the dropout, the number of hidden, and the number of layers. So in the meantime, I'll pause the video. So it has been done, and we can see the best combination we got is for dropout is equal to 0.3, number of hidden neurons is 256, and the number of layers is 1. And we can experiment more, and now we got the best score as 0.877. Yes, which is pretty good with just 1 layer, and we can experiment more on that. So this basically ends this tutorial. If you like my video, please subscribe to my channel. I'll be putting up more videos. Thank you.